In September 2015, the attention of the entire world, not just the scientific community, was captured by the discovery of a previously unseen phenomenon. For the first time, astronomers witnessed the collision of two black holes. They had been a pair for millions of years, but eventually merged into a single, larger and more massive black hole, disturbing space-time itself in the process. The traces of this event traveled through the universe for more than 1 billion years before reaching the most sensitive detectors ever built by humans. Thus, scientists learn not only to see the universe but also to hear it. What are gravitational waves and how do they affect us? And why does this newest field of astronomy receive so much attention and resources? Today we will discuss all of this. I think the story of gravitational radiation should begin with this photograph. This is one of the two largest and most famous gravitational wave observatories in the world, which are truly marvels of engineering and high-precision construction. I will explain why a bit later, but for now, let's focus on its shape and name. This is LIGO, an acronym that stands for Laser Interferometer Gravitational Wave Observatory. Despite the word observatory, as you can see, there is no large dome hiding a telescope or any dish that receives radio signals from space. That's because LIGO is not an electromagnetic observatory. It does not work with any part of the electromagnetic spectrum, neither visible light, nor radio or X-ray radiation, nor gamma rays. Yes, of course, some sources of gravitational waves can emit electromagnetic waves, but LIGO doesn't necessarily have to detect them, because gravitational waves are not part of the electromagnetic spectrum. They are a completely different phenomenon. Technically, even you emit gravitational waves when you accelerate in any way in space. The same goes for apples falling from trees, cars on the road, airplanes in the sky, and other things that gain speed. However, the masses and accelerations of all these objects are too small to generate significant disturbances in space-time. The greater the mass or acceleration, the stronger the gravitational wave. This idea was proposed by Albert Einstein in 1916 as one of the consequences of his general theory of relativity, published a year earlier. Einstein showed that gravity is not a force in space, but rather a manifestation of the curvature of space-time, which arises due to the presence of massive objects. This concept is perhaps best summed up in a single sentence by John Wheeler, a well-known theoretical physicist. He said, "Mass tells space-time how to curve, and space-time tells mass how to move." It is important to note that by incorporating the concept of space-time into physics, the general theory of relativity effectively rejects the idea that space is a rigid, immovable structure, and that time is absolute and flows unchanged. The mathematics of general relativity allows space-time to stretch, twist, and compress. Now, if gravity is actually curved space, how does gravity move from place to place in our universe? Well, the special theory of relativity imposes a strict limit on the speed at which information can be transmitted, which also applies to changes in mass. For instance, if we imagine that the sun and all its incredible mass suddenly disappeared, this information would be communicated to different observers no faster than the speed of light. This means that the Earth would continue to orbit around the empty space for another 8 minutes before the information about the change in gravity reaches us. Thus, gravity can propagate at the speed of light, and this fact leads us to the inevitable concept of gravitational radiation. After all, if gravity does not propagate instantaneously, then how does it propagate? Einstein tried to show this in his calculations of gravitational radiation. He didn't succeed at first, but through trial and error he eventually arrived at the desired result in the form of the so-called quadrupole formula. This formula demonstrates how gravitational waves arise from a system of accelerating masses, much like electromagnetic waves arise from a system of accelerating charges when the quadrupole moment of their distribution changes. In other words, matter that undergoes changes in its velocity or mass causes disturbances in the fabric of spacetime in the form of waves. These waves travel throughout the universe like ripples in a pond, moving at the speed of light. Yes, the analogy with water waves is quite illustrative, but let's not forget that it lacks one dimension. just like most animations, like the one you see on the screens. Space is not a smooth surface of a calm lake. It extends in all three dimensions around us, and gravitational waves move in the same way. There is another difference between the surface of a lake and the fabric of space-time. The latter, though subject to deformation, is still very rigid, so it does not bend easily, and its waves are, accordingly, not very large. Moreover, gravity is not a force capable of creating large ripples in space-time, as it is the weakest of all the fundamental forces of nature. Therefore, gravitational waves are extremely small, super small, and that is why Einstein believed we would never detect them. But it turned out that by focusing on astrophysical objects, the most massive objects in the universe that move with the greatest possible accelerations, and using advanced technologies, there is indeed a chance to see them. Detecting them would be very important because these waves can carry information that electromagnetic astronomy cannot provide, including clues about the nature of gravity itself. In fact, what is called a gravitational wave is a short-term deformation of space-time, stretching and compressing it at right angles. In other words, the distances between objects rhythmically increase and decrease depending on the frequency of the wave. Here, an interesting question may immediately arise. What does such a deformation mean for matter? Do gravitational waves cause objects in space to deform? In other words, can they stretch and compress us? Well, it seems that the answer is both yes and no. We are made up of atoms, which themselves are mostly empty space, with a few electrons and protons scattered within. So, the stretching and compressing of space would seem to apply to us as well. However, it is important to remember that the atoms in our bodies do not float freely in space. They are bound together by electromagnetic forces. Thus, the extent of our stretching depends on how much stronger gravity is compared to atomic bonds. Since we have already understood that gravity is the weakest of the four fundamental interactions, it seems that it indeed loses, and neither the Earth nor the cats on it will be deformed. However, in reality, things are even more interesting. The amplitude of gravitational waves is a very small value, and that's putting it very mildly. The oscillations caused by a gravitational wave that reaches Earth from the largest astrophysical monsters amount to about 10 to the power of -21 meters. This is so small that it can be compared to the size of a component of an atom, such as a proton. In fact, it is about 10,000 times smaller than the diameter of a proton. Therefore, there is almost no point in talking about any impact of gravitational waves on matter. Oscillations that are thousands or tens of thousands of times smaller than the size of a proton simply mean that gravity and electromagnetic forces do not conflict with each other. On the atomic scale, there are no oscillations. Technically, we do indeed stretch and compress with space, but to such a minuscule extent that it is as if we don't stretch at all. And this is precisely the magnitude that astronomers are trying to detect, which is why it is such a challenging task. However, it is important to understand that the amplitude of oscillations depends on the distance to the source. Therefore, relatively close to the source, gravitational waves can reach millimeters, and this already seems to be a serious destructive force which, depending on the frequency, could cause a lot of harm to your body. So, it's better to keep your distance. Before discussing the instruments that humans have built for such incredibly precise measurements, we should first talk about the sources that emit these waves and how they behave over time. As is well known, the universe is filled with a multitude of incredibly massive objects that are capable of experiencing significant accelerations. These could be pairs of black holes or neutron stars orbiting each other, or a mixed scenario where a black hole and a neutron star form a binary system. Naturally, each of these phenomena generates its own characteristic set of gravitational wave signals. Since binary systems differ from each other in terms of the mass of their components, their orbits relative to each other, and their distance from Earth. However, they all share one common feature that is imprinted in gravitational waves. Sooner or later, pairs of neutron stars or black holes collide with each other. But why? Shouldn't they orbit in their systems forever since nothing is stopping them from doing so? It turns out there is something, The gravitational waves themselves are the reason these objects inevitably meet. This is a direct consequence of the fact that gravitational waves are not just an abstract concept that has no effect on the surrounding world. Instead, they are a very real physical phenomenon that carries energy. But if gravitational waves carry energy, then the objects emitting them lose this energy. If this is a binary system of compact objects orbiting each other and emitting gravitational waves, they will lose energy due to their angular momentum. This means they will not orbit each other forever, but will gradually get closer and closer until they have no choice but to collide or merge into a single object. This particular feature of gravitational waves affecting binary systems helped confirm their existence for the first time. In 1974, two astronomers, Russell Hulse and Joseph Taylor, discovered a binary pulsar 21,000 light-years from Earth using the Arecibo Radio Observatory. Since pulsars are neutron stars emitting radio signals, general relativity predicted that this type of system should also emit gravitational waves. So, Hulse and Taylor decided to test Einstein's prediction. They began monitoring the radio emissions from this system to determine whether the orbital period of its components was changing over time. It took astrophysicists only 4 years to confirm that the period was indeed slowly decreasing. The two objects were indeed moving closer to each other at a rate precisely predicted by general relativity. For their discovery, Taylor and Hulse received the Nobel Prize in Physics in 1993. Since then, many research groups studying the radio emissions of pulsars have found similar effects, and at that time, this was the main evidence supporting the theory of gravitational waves and general relativity as a whole. However, all these confirmations were indirect, merely hinting at the existence of gravitational waves. One of the greatest discoveries in astrophysics and science, in general, was their direct detection in 2015, when the LIGO observatory physically detected ripples in space-time. Gravitational waves from a pair of black holes 1.3 billion light-years away traveled through the universe and appeared in the data of the most sensitive detectors in the world. This moment forever entered the history of science and effectively marked the beginning of a new field of astronomy.